In this lecture, we're going to work through an active example of a static analysis. And before we do that, let's first review Newton's second law. And Newton's second law explains the interaction between the kinetic side and the kinematic side of human biomechanics, where we have forces on the left-hand side and a kinematic variable on the right-hand side. And I want to introduce a new type of notation that we'll use every now and then, is that when we have a variable such as a in this instance, when we draw an arrow, a diagonal arrow through a, and at the tip of that arrow we put a numerical value, in this case 0, what we're stating here is that acceleration goes to 0. So we're going to set acceleration to a value of 0. And so with a static analysis, the acceleration value of 0 indicates the system is at rest. It's not moving. Now, if a system is moving at a constant velocity where it's not experiencing acceleration, that would be a static condition as well. But in our situation here, we're going to be specific to systems at rest. And when we see that we set acceleration to 0, a static analysis is simply a special case of Newton's second law, where on the left-hand side we see that we have a number of forces that act on an object, and the summation symbol indicates that we're going to add up, mathematically add all of those forces. And on the right hand side, the sum of those forces will equal to 0, and that indicates that the system that we're dealing with is at rest and is not moving. So we're going to carry that forward to a static analysis of a typical activity here that we'll address here shortly. And an important aspect of the static analysis is what's called the free body diagram. And this is a diagram that simplifies a complex system that will allow us to imagine or to depict all of the external contacts and hence all the external forces that are acting on that system or that object. And we're going to use vectors to represent those forces on the free body diagram. So in this example, we have a patient performing a rehabilitation exercise. This patient is holding her leg in a knee extended position, and the elastic band around the foot that's tied to the table is providing additional resistance, forcing the quadriceps femoris muscles to contract even more. But in this example, our only interest is with the right leg and the foot, rather the right lower leg. And so we begin the process of isolating our system of interest, which in this case is the lower leg and the foot, but we see a very non-symmetrically shaped, oddly shaped lower leg and foot that makes it difficult to analyze quantitatively. And so what we do here is that we now develop a model of the lower leg, something that adequately represents it yet is much more simplified. So I'm going to use a rigid bar to represent the lower leg and a triangle to represent the foot. And this will be the start of our free body diagram. And the objective here with the free body diagram as part of the static analysis is to calculate all the external forces and something I'll introduce and review again here, moments of force that are acting on this system. So once again here, the free body diagram is that simplified diagram that I have isolated here that we're now going to use to represent the forces that will influence the behavior of this system. The first step is always to draw our frame of reference. Because our leg is perfectly horizontal, then we can use our standard XY coordinate system where anything directed to the right that horizontally is considered positive. Anything directed upward vertically is positive, and counterclockwise rotations are also indicated as positive. So now we'll start to represent the forces acting on the leg, and I'm going to draw the weight of the leg somewhere in the middle. That's at what we call the center of mass. Looking at the diagram on page 3, we saw that there was an elastic band tied around the person's foot, and it's going to be pulling along the actual band, where the band actually is. We know that in order to hold this position, the person's knee extensor muscle group, the quadriceps, must be producing force, and we know that that force is transmitted through the patellar tendon, which has an attachment onto the tibia, not at the joint, but just distal to the joint. That's going to be an important aspect that we'll come to a little bit later. But the leg doesn't actually move. It doesn't translate in one direction or another. The reason that the leg doesn't slide to the left here is because we have another force that's restricting this linear motion to the left, because we see that the quadriceps is attempting to pull it. Because of the anatomy and the structure of the entire leg, we have the femur, which provides what we'll call a reaction force, but we'll label that here on the next slide. So in conducting a static analysis, it's always important to go back to our fundamental steps. The first step is to draw the free body diagram, and although we haven't labeled the forces yet, that's going to be an important aspect that we'll do on the next slide. We need to draw our coordinate system, because our coordinate system will dictate how to interpret all these different force vectors that we'll be using. Once we have that all set up, we'll apply Newton's second law that is specific to a static situation, and complete the equations of equilibrium. And then once we have the equations of equilibrium all set up, then we can solve for all of the unknown forces, as well as the directions of those forces. So we're going to redraw our free body diagram here, but we're going to give those forces labels. And so just to review our steps once again, we're going to draw our coordinate system that we just carried over from slide number 4. We always typically draw the weight of the system, and that weight of the system is always has a point of application, is always centered through the center of mass, and is pointing vertically downward. And I'm going to label this with uppercase W for weight of the lower leg and the foot, and that's going to be equal to the mass of the lower leg and the foot times the acceleration due to gravity, which we use 9.81. We have the elastic band tied to the end of the lower leg, and I'm just going to label that F with a subscript band to give that a unique label. This band will form a 20-degree angle from the lower leg that we'll use shortly. The force generated from the quadriceps femoris muscle that gets transmitted through the patellar tendon will actually create a pull or a tension at its point of application. And I'm going to label that FPT for a force through the patellar tendon. And the last force here is what we call the FR, subscript R for reaction force. Now it's important to note here that the reaction force, we don't know at this point if it's the correct magnitude or the correct direction as I've drawn here. FR will be dependent upon the combined effect of all three of these other forces. So once we work through our equations of equilibrium, we'll then have the ability to determine the correct magnitude and direction of the reaction force. We know it's there, but we don't know its direction. So what I've done at this point is I've made a guess that the reaction force is going to be at this particular in this particular direction. And then as we work through our analysis, we'll make the necessary corrections if indicated. Now, to move forward with a static analysis, we need some actual data here. So the mass of the leg, we'll set that to 4 kilograms, and these are data that would be given. The length of the leg and the foot combined is set at 40 centimeters, and note here that we always express it in meters. The force of the elastic band coming through the elastic band was measured and is determined to be 150 newtons, and that forms, as indicated on the diagram, a 20-degree angle from the lower leg. The COM is the center of mass, and that's the point where we estimate the weight is concentrated for the lower leg and foot, or rather, around this point the weight is distributed. And the center of mass is located, we'll say at this juncture, halfway from the proximal part of our system to the full distal part of our system. And half of 40 centimeters is 20 centimeters that we convert to 0.2 meters. Now, there are more anatomically accurate measures of center of mass, but at this point we'll just go with 50%. The insertion of the quadriceps femoris muscle through the patellar tendon is estimated to be 5 centimeters or 0.05 meters distance, the distance from the joint. So this very small distance here is 5 centimeters, and that's an important consideration because if FPT had a point of insertion right at the joint, it would not be in a position to produce a rotation. So even though it's not very far from the joint, it's now in a position where it can create a rotation about the joint. And it's also important to note that the angle of insertion is 15 degrees. So not only do we need to know where it inserts, but what the angle of insertion is. And this angle is going to reflect the direction of the force vector through the actual tissue, through the patellar tendon. So this will end the first part of our example of our static analysis, and now we're set up to actually step through and begin the process of solving for our unknowns.